Okay, good afternoon, good day, good night to everyone. It's our pleasure here on behalf of the IEEE South Brazil Joint Chapter, which is a joint chapter of the Solid State Circuit Society and the Electron Device Society, to have this distinguished talk, the first of a series that this chapter is organizing. You're most welcome to join us in this YouTube channel. I encourage you to subscribe to the channel because you'll be able to get warnings and tune in for the next distinguished talks. The next one, as you see here in the screen, is slated for July 9 at 1:30 p.m. Brazil time. And a few words about IEEE have been given to you already. You all know IEEE. We, members of the Solid State Circuit Society and the Electron Device Society, encourage you to join IEEE and also join at least one of those two chapters. And if you are South Brazil region, South Brazil section member, please join the chapter also. Okay. So let me introduce. Now the speaker. We have the pleasure to have as distinguished speaker and give this distinguished talk this afternoon live Professor Jorge Fernandes. A few words about him. He is a master and PhD degree from the Instituto Superior Técnico, is engineering school in Lisbon, at the University of Lisbon. And he joined the faculty of the Department of Electrical Engineering at the IST Lisbon in 1990. So he has, 3 decades of a career in teaching. And he was a visiting professor a visiting scholar at the University of Delft, and Delft University of Technology, and also in Columbia University. His current research interests include analog, mixed signal, and RF circuits, with an emphasis on autonomous sensor circuits and low-power RF front-ends. He is very known for his prolific developments in these fields related to circuits and systems and integrated circuits. He has been general co-chair of the ISCAS 2015. He co-organized, co-chaired in that year in Lisbon. So with that being said, welcome, and also thank you, Dr. Jorge Fernandes, for agreeing to deliver this distinguished talk. I'm very sure that the audience here will be pleased to hear you in the next 60 minutes. At the end, after your talk, there will be questions that you can answer, questions that you, the audience, can send through the YouTube chat. So the floor is yours, Professor Jorge Fernandes.
Thank you very much, Professor Sergio Bampi. Thank you for the kind words and for the introduction. I would also like to thank you and Philippe Baumgarts for the kind invitation to participate in this series of talks. I would also like to thank the chapter, the joint chapter of Solid State Circuit Society and Electron Devices Society in South Brazil. My talk will be entitled Low Power Circuits for IoT. And before I start, I would also like to do some short acknowledgements. As you may know, this is I will present some, let's say, tutorial valued view of IoT, personal view, but also work from many of my colleagues, students, collaborators, colleagues. So I have here some of them, past students, actual students and collaborators, and also many others. I would also like to thank to mention some of the projects that we are involved in, the national projects and European projects that also contribute to some of the circuits and the work that I will present here. So now starting with the talk itself, the outline of the presentation. will be divided in 3 topics: motivation and driving factors. And then I will jump into circuits, and I will talk more about power harvesting circuits, and also have a bird's eye view on ultra-low power RF emitters, where I will mostly focus on impulse radio ultra-wideband circuits. So going into the motivation and driving factors, my view of it is that when I started as a student, bipolar and CMOS was being getting generalized, and the previous technology was mostly based on bipolar circuits. And the study of the circuits on electronics were divided in 4 different kind of circuits. So we had the RF circuits, we have the analog circuits, the digital circuits, and also the power circuits. And the techniques and the circuits had different approaches in the way they were designed. Well, later on, CMOS has evolved a lot, so there was a kind of a mix between bipolar and CMOS, and that led to an increase in the digital domain, in the digital signal processing domain, and less importance on the analog domain. So, and the reason for that is that CMOS transistors, they can produce very good switches, and with very good switches, we can produce digital circuits that are very easily built. If we have a switch that we are able to connect the output node to VDD, we have a 1 at the output. If we have a switch that is able to connect the output to 0, we have a 0 at the output. So this will lead to a very simple inverter just with 2 transistors and with several huge advantages. The first one is that the static power is 0, which is an advantage over bipolar digital circuits. And it is a huge advantage that will make CMOS become predominant, and also digital signal processing become predominant. So with this static power close to 0, just the leakage of the circuits, it was possible to have very large digital circuits. So then we are concerned about dynamic power. So the dynamic power is the power that we need to change the state of a digital circuit. And if we look at it, it's kind of easy to obtain an expression that shows that the power used to change the state of a digital gate at a certain frequency is given by the load capacitance times the power supply squared times the number of occurrences that I will represent here by F, meaning the frequency of the clock of the circuit. So this is a very simple equation that will also allow us to see some recent developments are in fact greatly they are due to this expression. So if we move on to, So if we move on to the motivation driving factors, we see that the first step was to join analog and digital circuits together in the same die. And by doing that, we were able to, we were requiring some less common blocks like ADCs and digital to analog converters that now became very important circuits, and one of the most important towards the design of a whole system on a chip with digital signal processing. And going on with this expression, we see now that what we really want to do in order to reduce power consumption is to reduce VDD because it's squared, and in a second order to reduce the load capacitance of the gate. And to reduce the load capacitance of the gate, the solution is clearly to reduce the size of the transistors, because the load of a gate is the input of the gates to which the gate is connected. So we will need to reduce the capacitance, and this is obtained by shrinking the transistor size, and we'll try also to reduce the power supply. As you all know, TTL logic cells were with 5 volts, then digital circuits jumped to 3.3 volts, 2 volts, 1.5, 1 volt. Now we are even designing with 0.5 volts in a VDD. Regarding the capacitance or the reduction in size for the transistors, we could see that in a brief view on this slide, which is based on the Moore's law. We could see how they have evolved through years. So I kept everything in nanometers so that we have a clear view of how it has evolved from 1971 until today. So transistors were 10 microns or 10,000 nanometers minimum length, and they are now around 5 nanometers of gate length. So when we see this, we can see that the reduction in size was really incredible. It's really a huge evolution. This evolution has been always in exponential rate, which is also amazing that the technology is being evolving with an exponential rate for so many decades. And of course, in the last few years, the transistors also evolved. The technology is not only bulk CMOS, but also mostly SOI and FinFET transistors that were able to keep on with this Moore's law pace. So when we look at this, we see that it's not only the L that reduces, it's also the width of the transistor that reduces. So the capacitance, in fact, is reduced more than a linear relation with the length of the transistor. So if we look at these technology trends, we see that the length and the width of the transistor is reducing a lot, which means that the transition, the FT of the transistors has increased a lot. So now with CMOS, it's possible to design circuits at gigahertz, which was not possible before. And this brought several different domains together. So now we are allowed to design RF circuits with lamp circuit design techniques, and also to use feedback techniques in these circuits, explicit feedback techniques, so that the RF circuits are designed more in an analog way, so to say, than they were before. And we could let's say, expect more to design the circuit as the previous RF circuits when we are connecting it to the input and to the output of the circuit. The other thing that also has evolved is integrated inductors. So one thing that they have in their disadvantage is that usually the inductors are not scalable. Without being scalable and with low values of inductors and also low values of quality factor, this means that when we look at inductors and we see the transistors shrinking, we can see that the size, the die area size of an inductor is now becoming much larger than, let's say, an array of transistors. In the figure on the right, I have an inductor with 1.5 nanoampères, and I have an array of 10,000 NMOS transistors with minimum dimensions in the 40 nanometer CMOS technology. So you could see that, in fact, it's not the number of elements that counts now, it's the area, and because the cost is related to the area. So this favors a lot that we can do digital circuits instead of conventional analog circuits. So we have this degree of, this extra degree of freedom that we can use more transistors as we want. And if we look at this third bullet, we see also something related with the cost. So when we compare a 180 nanometer technology with a 28 nanometer technology, we could see that there is a huge increase in cost, obviously, but the foundries also argue that as we can put more gates into the same area, in fact, the cost per transistor is smaller. Okay, this is not the case every time, but it's a good guideline. And it's also a good guideline to say that that does not happen, for instance, for inductors, where if we use a clear inductor in a more advanced technology, in fact, the inductor is getting more expensive than before. Okay, so now that we had this RF, analog, digital, and power blocks, we can say that we could get them all together because now we are able to design RF circuits at 2.4 gigahertz or something like that at those frequencies already with conventional CMOS. We could also do the digital processing with CMOS, and we could do advanced analog also in CMOS. So I must say that this is not totally an advantage because we are reducing the power supply. And by reducing the power supply, the analog becomes much more difficult to design because the rail-to-rail voltage is smaller, the linear region of the circuits is smaller. Also, we could not scale the VT of the CMOS transistors in the same way, so we also lose excursion there. So the analog design is now more demanding. However, even with all these constraints, analog design has evolved a lot, and many new circuits and new topologies have been deployed over the last years. And with all this together, we were allowed to have an internet boom. So we were from the point where we had a telecommunications boom, where we could connect people with cellular phones, mobile phones, and now we had the internet boom that we are experiencing now, where we have connected all the computers. So what is the next step, or what is already ongoing? And someone has called it IoT, Internet of Things. So by joining sensors to these elements, and sometimes not based on not silicon-based sensors, and but connected with ASICs silicon-based, we could do many wireless small circuits that could be deployed largely. So this IoT challenge is to connect all things. So not only computers, not only people, but that we can have all things, all appliances connected and controlled by some means of an application. And if we look at some of the reports, some of the forecasts of how this Internet of Things will influence the market of microelectronics, we could see that in fact the huge advance will be on short-range IoT, where it is expected that appliance will raise from 5.2 to 16 billion devices. While when you see the PC, laptops, tablets market, it's not expected any increase. Mobile phones, well, also almost no increase, and fixed phones, it's already decaying. So in these conventional applications, let's say that almost everybody already has one. So where we have market to increase is on these small appliances that are connected. These are divided in wide area IoT, which is usually the large deployment nodes, and short range IoT, which is the small devices that we carry with us and that are short range monitoring devices. And my talk will be mostly on circuits targeting this short range IoT hype. And of course, the goals that we have are the same as before. It's low power, low area, low cost, which is always the things that we are looking for. So this is what I believe would be a general low power IoT sensor node. So we try to have it wireless powered to be totally independent. So for that to happen, we need to have some kind of energy source, and we need to to transform that energy source into electrical power. So we can do that by an inductive link, an RF link, an ultrasound link, a thermal link, and so on. And we have to have the transducers to do that. Once we have that electrical signal, the electrical power, we have to do some power harvesting, maybe a regulator if we want to have a clean, stable supply voltage. And this supply voltage will be able to bias a core circuit. And this core circuit will have, of course, a processing unit, some ADC and digital to analog converters to interface with some sensor or actuator that will be the main objective of the sensor node. Finally, if we want to have some communications capability, we could have an RF wireless link or some other kind of communication link and an interface with the exterior. And if we look at it, all these boxes that are on the right side, the black boxes, they can be built with integrated circuits, with conventional silicon-based circuits. And my presentation will later on focus on power harvesting and RF wireless, which are the interface electrical circuits on this wireless sensor node. So now going into the power harvesting circuits, I will do a short revision of the state of the art of the power harvesting circuits, and then I will show some circuits that we design ourselves and bring some of our own experience to this talk. So when we look at power harvesting circuits, the idea is to have self-powering. And we already had self-powering. We used batteries. They have evolved a lot, and they are most used. So they are really responsible for the market increase of wireless appliances. They are miniaturized, they are reliable, they are independent, and they have an adequate voltage that many times defines the jumps in voltage that we have in the digital circuits. And the things that limit its continuing growth is that usually they are expensive, they are bulky, so it's very hard. If we reduce the size of the battery, obviously we are reducing the autonomy of the equipment. They are bulky, they require replacement, and they require disposal because they have chemicals inside. We could go further on and think that if, for instance, they are used in medical devices and to be applied inside the human body, for instance, we even have to have other kind of attention and care because we have to make sure that the battery never leaks into the body. So usually they have to be placed in some titanium boxes. So with all this in mind, if we are able to send energy into the circuit in real time and have the circuit operating in real time, that would be a huge advance and a huge benefit. And that will allow for many other applications to come. So now I will talk about energy harvesting, or also known as scavenging circuits. So the idea is to extract energy from the environment and convert it to electrical power. That's the main idea of scavenging. But energy harvesting can also have, we can also have a dedicated source of power. The only difference is that it's not wireless wire connected to the circuit. Its goals can be of different type. It can be just to recharge or to extend lifetime. It can be to replace or reduce the size of batteries. So Still, we can have batteries if we are not able to fully replace the batteries. The idea is it depends on the application and obviously on the amount of energy that we have available after harvesting. So by doing this, we also provide self-powering capabilities, or we enhance them, and we allow again for fully autonomous devices. The main difficulties of this source of energy is that usually the power available depends on the actual ambient excitation. So it depends on a lot of factors, and this will cause that the amplitude of the source signal is not stable, so it can vary a lot. And the average output power can be random, fluctuant, or intermittent nature, so it depends on a lot of many external conditions. So this is what we need to see as the difficulties on applying this kind of technology to our circuits. So therefore, there are three main goals. First one, obviously, is to increase efficiency. So our source of power is usually very limited, so the efficiency is very important to ensure that we have the maximum power availability to power our circuit. We have to ensure that it has a low cold start. By cold start, I mean when the circuit starts from zero, our appliance is completely without any charge whatever, and it has to start. So there is a minimum power level that will allow the circuit to become alive. And then to reduce the dead zone, which is usually less restrictive than the cold start, because once the circuit has been powered, we can use techniques to have the transistors operating in better regions, in regions where they are more efficient, and then we can make the circuit work with better properties. The usage can be of continuous mode or duty cycle mode. So due to the scarce energy that we can harvest, it's very common that these sensor nodes are highly duty cycled. And we can imagine many applications where we don't need to take data or to make readings and so on at a very high frequency. In fact, they can be very, very extremely low frequency. Okay, so if we have to do a classification, and I have chosen the four most important sources of energy, the most common, which is solar, thermal, vibrational energy, or inductive RF energy. And I have did some survey and look at the outputs that happen mostly for these four classes of energy to be harvested. And well, of course, based on what is our target on this talk, which is small equipments, we see that the power is mostly in the case of microwatts to a milliwatt. And let's say with a few volts, if we have solar or thermal sources, usually we require them to have a DC-DC conversion because the source is already a DC voltage. If we have vibrational, inductive, or RF, we need to have some AC to DC conversion. And we will use this to, after we classify the sources, we will not care that much about the transducers, and we will care more about the circuits. So going first for this solar and thermal DC to DC converters, we see that we can have a photovoltaic cell or a thermal cell. And when we see usually the circuit itself, we have, well, let's say an input capacitance, some circuit with a charge pump that can brings the voltage somehow up, an output capacitor that acts as a buffer, and the switch that will connect the load to this voltage source somehow. Well, this is the top part of the schematic. but of course we need to control it. And to control it, we need some architecture. And because the initial input energy source has such a large variability, usually we need some control circuit. And this control circuit usually is based on a maximum point power tracker architecture to make sure that we obtain a voltage that is stable at the output. And this circuit has to operate with very, very extremely low power levels. If we see here a more clean figure with less components, we could see that on this figure, we have a ring oscillator, a charge pump, some intermediate voltage here that will power a ring oscillator, and then when it has enough power, it will enable the ring oscillator. And this is the kickstart clock, and then it means that we have enough energy to feed the load. So these techniques are commonly used, and we need to have circuits that operate with very, very low power. In fact, it's interesting to have this talk here. There is a paper from Machado et al. From Universidade de Santa Catarina that shows that we can have oscillators operating even with millivolts of range. So when we look at it, usually these blocks require a charge pump, a DC to DC booster, a maximum power point tracking circuit, some clock and feedback that requires kickstart circuits, and obviously it obtains a voltage. That means that the cold start voltage is higher than the dead zone voltage. If we go for vibrational RF or inductive links, we are talking about an input signal, which is a signal at a certain frequency. So we have to convert this signal towards a DC voltage. This is usually done by a matching network that adapts the circuit to the source of energy. And in the example, I have an antenna and I have an RF matching circuit. Then we have a rectifier. So once we have some sort of sine signal or a varying signal, we have a rectifier. And finally, a processing unit that can somehow control this circuit. So at the output, we will have some DC output voltage. For the vibrational circuits, these are mostly the elements that will happen. So for RF and inductive link, it's more or less known. So it's antennas or inductors connected in a way that act as a transformer. For vibrational circuits, usually it's piezoelectric circuits or some vibrational electromagnetic. It can be vibrational electrostatic by means of CMOOTs, for instance, capacitances that change their capacitance, and therefore, being the charge maintained, they will change the voltage at the outputs. So it can be some CMOOT pressure MEMS, some vibrational electromagnetic, like the one that we have here, where we have some coil and magnet, and by moving them, they will produce some output voltage. And of course, we can have a mechanical electrical model to simulate these piezo harvesters or vibrational circuits. And when you see what happens afterwards, is the same as what happens with RF circuits. So usually we have some rectifier circuit or some voltage doubler circuit where we can increase the output voltage tailored to our applications. And finally, we have some rectifying circuits that is here represented by a capacitor. So this can be done in a variety of things. This is a cantilever, which is also a way to obtain some vibration, where we have some structure where if we apply some energy to the edge of it, it will oscillate at its own oscillation frequency. Okay, so this figure I borrowed from Zen, from the Solid State Circuits journal to 2017. And it's a very interesting figure because it summarizes, let's say, the most of the techniques that have been used with this kind of circuits in order to optimize the energy to be harvested. So we in all of them we have this transducer here that is modeled always by the same circuit, and then we see what happens. So we can have only the oscillation due to the circuit, but we can also increase its range by having a switch here, or by having an inductance that will somehow amplify the switching of the signal, or some other scheme with switch capacity with a switched capacitor that will act somehow as an inductor and will replace the inductor and will allow for a maximum output power for the same signal. And we can see here that in fact all these techniques have improved the energy that we can harvest from the same source. But on the other hand, obviously we will need some control circuit, we will need some extra circuit elements, which will always be let's say, the penalty or the cost of improving the efficiency of the circuit. So if we look at an RF circuit, the solution is more conventional. So usually we have an antenna, so we have to adapt the antenna, and we have to try and provide voltage boosting, because the voltage at the antenna output is usually of a small value and not high enough for our application to run. So we will need also to try and improve that. These are some kinds of RF matching networks that can be used. So we can use an LC match, a T match, some transformer match. So there are many techniques that have been also used in our FID tags, like direct antenna matching, and in microwave techniques using microstrip or stubs designs in order to obtain the matching network. So what is the degree of power that we should expect? So if we look at this, all these sources of power, we believe that RF power harvesting is probably the most demanding, where the power levels are smaller, especially if we really want to use not dedicated sources, like sometimes we use in RFID. If we want to use, for instance, if we want to obtain energy from a Wi-Fi network that is already there, that's 2.4 gigahertz, then we, at 10 meters, we already have only received powers in the order of microwatts. And when we see that, and we already have a low efficiency of our circuits with these power levels and these very low voltage input levels, this would mean that the available power for our circuit will be even much smaller. So this is how we can rectify this kind of signals. So what I have here is a very simple rectifier, only with the diode and the capacitor. And if you look at it, we lose let's say, the voltage drop on the diode. So if the voltage is very small, the circuit does not behave as we are used to, does not behave as we have studied in conventional classes of circuit analysis and so on when we studied diodes, where when these circuits were applied were for voltages that were much higher than the diode voltage. Sometimes we even neglected it. Now we are looking at voltages that are much smaller than the on voltage of the diode, so to say. So then we have to do a different analysis and to look at the different circuits. We will definitely need to do two things. We need to increase the output voltage, and we need to reduce losses, because now the circuit has losses on the on state and on the off state. So how can we increase the output voltage? If you see at this slide, I have here two circuits that are multi-stage topologies. One is the Grain-Apper multiplier from 1913. The other is Dickson charge pump from 1976. If you look at the first, it was really used in very extremely high voltage applications. But these techniques are still usable if we are able to have good diodes. You can also use a charge pump or voltage doublers. This is the most common circuit that has been used in order to, as a charge pump, in order to increase the voltage. It's called the modified Dickson charge pump. And it's represented here by a sequence of diodes and capacitors. And on each node, the voltage will increase by a certain amount. And therefore, we will have, if we use n stages, we will have the voltage, the input maximum voltage, minus the diode voltage drop times the number of stages. Okay, so here the main issue is that in microelectronics, we usually do not rely on extremely good diodes. And we also have the problem that we are facing very extremely low voltage values. So we can implement this circuit by using other circuit elements like bipolar transistors or CMOS transistors. In our case, we are going to use MOS transistors to design the circuit. And we are going to design them usually by using a transistor as a passing gate circuit. But assuming that we are now having a transistor with a passing gate, but it's not also as we are used to look at it in conventional electronic classrooms, because the gate voltage in a circuit that is acting as a power harvest, we don't have a high gate voltage. So in fact, we will have a circuit that will have some, let's say, resistance, that will have some current flowing in this direction. And when this voltage is higher than the input, the current will go in the reverse direction. So part of the current is charged in the capacitor. Part of the current is discharged through the transistor, because now we don't have an ideal perfect switch. So if we look at the state-of-the-art review, how can we improve this scheme? We can use, well, Schottky diodes, we already talked about them. We can use batteries to increase the VGS of the transistor, and therefore to increase, to improve the behavior of the NMOS transistor as a switch, as an on-off switch. We can use a pre-charge phase and use a capacitance, which is, let's say, a more simple solution in terms of circuit. We can use a differential rectifier, and then we have some kind of signal also applied to the gate of the circuit. Or we can have some self-compensation that means that we can connect the output, the gate voltage, to higher nodes on the chain where the voltage is already higher. So from each stage that we are using to amplify, to increase the output voltage, we can benefit from there. So once the circuit is starting, it starts to pump and to increase the voltages at all the nodes. And by increasing the voltage, it will benefit the first stages transistors and increase the efficiency and the characteristics of the circuit. This is shown here, where you see that we have connected the input of the rectifier to the gate, the bulk to the drain, and by using that, we can see what happens. This is the place where it is discharging, and this is what we lose. This is the angle where the circuit is charging relative to a sine wave input. So it will have some kind of steady state point where it will harvest, where it will charge during this period, and it will discharge during the angle that we have in red here. So how can we improve this? How can we make this circuit more efficient towards this application? So the idea is that both VGS and the source bulk terminals can affect the ID related curve of the transistor. So VGS strongly affects the transistor channel. The source bulk voltage, well, in a lesser mode, but it also affects the transistor channel. This can be improved, for instance, or can be enhanced even if we have, for instance, a silicon on insulator technology, where we can really improve the influence of the source bulk voltage on the behavior of the circuit. So we can improve the behavior of this circuit, and we have tried several things. We can see them when we have a voltage constant here, when we have a voltage constant between VGS and also a constant voltage between the bulk and the source of the circuit. And we can see the influence of these voltages on the circuit behavior. So mostly the difference between these two circuits is that the VBS here during phase 1 is 0, then it has a certain voltage. Now it's the other way around. During the charge phase, we can improve VBS, then reduce the VBS during the discharge phase. This is the advantage when we compare this first approach with the second approach that we tried. And we can see that not only we increase slightly the maximum when we compare both curves, I should show that the scale is not the same. Here is 80 millivolt. Here is 80 millivolt on this charge. So we have a higher voltage here. Also here we have a higher voltage on circuit 2. And when we change also the bulk voltage, we can shift it to the left. So meaning that the gate voltage then becomes more efficient earlier. So we can increase the behavior of the circuit with less gate voltage, and by at the same time applying a bulk voltage in a different polarity. If we look for some kind of techniques to exploit already a signal, not a DC voltage between the terminals, we have designed these free circuits or tested these free circuits. We have designed a circuit where we add also the input signal here. Where we add the input signal here, this is C1 with an varying input here. This is similar to C2 with a variable input here. And this is a new circuit, which is similar, let's say, to circuit 2, but with a signal here and a signal here. So when you look at it, we can draw the line curves, the voltage on the transistor with in these free circuits during a whole conducting cycle of the circuit, and we can have here the charge phase and the discharge phase. Well, again, the results are the same. We can increase the output and we can shift the output to the left. So we can do this by having a differential circuit. Now I will in a more faster way show some of the results that we have obtained. So we have these two circuits, C1 and C2. They are very useful for use with single-ended inputs signals. And we have C3, 4, and 5 that are better to use with differential signals. They require in-phase and anti-phase chains, so in fact they require double area, but they have higher efficiency. They will have lower output voltage per stage, and they will require PMOS devices for a full implementation. This is how it works for the single-ended. You see that Here on the first stage, we are already grabbing the voltage from the second stage. Here we are grabbing the voltage from the third stage. Here we are grabbing the voltage from the fourth stage, and so on. So we can increase the gate voltage at each stage. If we do it differentially, we can do it again by exploiting, let's say, a differential version of the previous circuit, and then we can grab the voltage that comes from the other side and make sure that we exploit twice the voltage of twice the difference in voltage for biasing the circuit, also gaining a factor of 2. These are the results of the first prototype. So we used just C1 with 18 stages, and we did some integrated transformer matching. So the circuit was designed. You can see that the area mostly is due to the transformer. The circuit itself represents a much small percentage of the area. And we were able to obtain 1 volt with a 10 mega ohms charge at -4 dBm. And the circuit operated at 1.3 gigahertz. The second prototype, it's already a C5 circuit with first order gate bias and third order body bias. And we have used an L-matched network and working at 2.4 gigahertz. And we're able to obtain 1 volt at 1 mega ohm, so 10 times the current, with -9.2 dBm. And later on, we did a third prototype where we have used some low VT transistors. We did some T-matching, and we worked with UHF frequencies, ultra-high frequencies, around 900 megahertz. Again, the same circuit topology. And we are able to obtain 1 volt, 1 microwatt output, and an input cold start of -70.4 dBm measured. Okay, so this is already a very good result. Okay, so to give a very fast view, because I'm late in time, I will talk about ultra low power RF emitters, and I will only talk about impulse radio ultra-wideband. So impulse radio ultra-wideband was a very studied topic a few years ago. It was an alternative to narrowband systems. It was able to use signals that would cover a band from 3.1 to 10.6 gigahertz. And the idea was that the power levels were so small that for the other narrowband standards, they will behave as noise floor. The potential was to have high data rates due to the large bandwidth and to have low power due to the narrow pulses. Okay, so these kind of circuits have lost their momentum towards the main idea of having these high data rates, but I think that for IoT, they are still usable and they can present many benefits because they really are very low power. Okay, so if you look at it, when they were used for communications, also something that was not an advantage was that local regulations were different from FCC regulations, so there were some limits imposed by each country to the bandwidth, and to make standards was more difficult. But they are very interesting. They are based on baseband pulses of short duration, and by short duration means a few nanoseconds. That when translates into the frequency domain, it will mean gigahertz of bandwidth. Okay, so this is how we can do it. If we think of it, we can mix a square wave signal with a sine wave signal, and we can have a modulated pulse signal. If we do that with a Gaussian pulse, we can have a modulated Gaussian pulse. When we do a modulated Gaussian pulse, we have the advantage that in the RF frequency, in the frequency domain, we also have a Gaussian. And having a Gaussian has the advantage that we don't have side lobes. So if we go back here, it would mean that it's more hard to violate the band that protects GPS and all these other applications that have very, very strong protecting specifications to avoid collision. Okay, so this is more or less what we really want to do. Sometimes we obtain something in the middle. Okay, so the main idea here is that also for IoT applications, these things have changed a lot. So when we think about RF communications, usually we think about efficiency of the output stage. Excuse me. This is because the output stage was usually used to broadcast with very large powers, and the receivers were many receiving the signal. Now it's the other way around. We are concerned about the efficiency relative to the battery, and we have short-range circuits. So the communications power efficiency is not that important, not as much. And what we are really interested in reducing is the circuit's power consumption, the DC power consumption that will limit the battery life that we have. And when we look at trends, if we do a state-of-the-art thing, we can see that in receivers, the efficiency, which means the energy per pulse, usually decays when we increase the data rate, which makes sense because the receiver is always listening, so sometimes it has constant power. And if we have more pulses, that constant power is divided by more pulses. So this is more or less expected. When you look at transmitters, it's more or less linear. I mean, if we have more pulses, we have more power because the most of the power is spent on the pulse production. So when you go also in terms of processing nodes, we see that for the receivers, we don't have, let's say, any trend because we still have to have the same characteristics. While for the transmitters, it's usually easy to produce a pulse because the transistors are smaller. The power that we use is smaller. So again, when we reduce the process node, the transmitters benefit from it. So it's very this last reasoning means that if we want to have an ultra low power radio, it's usually for us to have a sensor node with a transmitter that uses this impulse radio to wideband. And we have a base station, which is usually something that has more relaxed specifications on power consumption that is going to be able to receive that ultra-wideband signal. But here we have less restrictions. So the transmission here can be of any RFID type, and the receiving, if we need to have some kind of programming of the node, can be of passive nature on the input. Also, the nature of modulation can be done in a very simple way. We have proposed this on an ISSCC paper of having a pulse that triggers the receiver circuit that now starts listening. And then if in a certain time period receives another pulse, it assumes that it is a 1. If it does not receive any pulse, it assumes that it is a 0. So this means that with 1.5 pulses, we can transmit a bit, which is also a very nice result. And this means that even for process variations and variability, if we have a large window here, we can assume that this signal appears slightly delayed relative. We just need to ensure that the guard band never goes below what it is expected. So there are some modulation schemes that can also make the circuits ultra low power. Okay, this is the circuit that I showed you before. It can be, here is a signal of the measured circuit. Here is how it operated. So this is the kickoff. Let's say this is the pulses that we transmitted. So when we transmitted a pulse like this on the other side, we received the pulse similar to this. In fact, is this one that I represented here. We have used an LC to have very low power, to have a very efficient circuit. Now, the problem was that to discharge the LC, because then we have some time that would make the circuit decays graciously towards 0. Instead of that, we also have to use the pulse supply. So we connect this circuit to ground, and we discharge the LC tank immediately. So now we have almost the same rising time and the same falling time. And if you look at it, it's not a square wave. Then it becomes something between a Gaussian modulated pulse and the square modulated pulse. Finally, this is a topology that we also presented for impulse radio ultra-wideband emitters that would benefit from other kind of technologies with smaller voltages and so on, which is to have such a control unit, an oscillator, and then a divider. So the divider will ensure that the circuit will start by itself. When it starts the pulse. So we have here the circuit, the pulse changing. And as the pulse change, at a certain point, the divider output will count the amount that we have decided to divide and change the pulse width that stops the circuit itself. So by doing this, we can do a circuit that it's totally digital. It can have a ring oscillator, although we implemented it with an RC oscillator, but it can be implemented also with a ring oscillator. And we can have a divider that can divide by 16, for instance, if we want to have 16 cycles of the signal itself. Okay, these are the results that we obtained. This is pulse layout results, not measured results. And we have tried to do it at a very high frequency, near the 8 gigahertz band, to get away from GSM as much as possible. Okay, so to conclude my talk, because I'm already over time, so IoT has many disciplines and specifications are application driven. Most promising subset are autonomous wireless sensor nodes. CMOS remains the enabling technology. I believe that it has a large infrastructure. The industry is well defined. The technology has very high yields in all aspects of it. So it will be very hard to find something that totally replaces CMOS technology. Regarding the circuit design and what I have presented, power harvest is a main research topic. Ultra low power will also remain a research topic. Ultra low voltage definitely will lead to digital-based analog circuits at all the vectors, all the implications of it. And I also think that IoT sensor nodes can benefit from large sensor arrays, namely these new MEMS that are built in an array style. And with this, I finish my presentation. I thank you very much for listening, and I apologize for exceeding my time.
Okay, thank you, Professor. Yeah, obrigado a você. Thank you very much. Yeah, it was a great talk. There is no overtime. You know, we are perfectly on time. We have a few questions that came into the YouTube channel of the joint chapter, Solid State Circuits EDS. And I have here the first question typed by Sandro Ferreira, who is also part of the coordinator of the chapter. Professor Jorge, in the beginning of the presentation, you suggested separate antennas, one for communications and another one for energy harvesting. And then we may also need a wake-up receiver and potentially another antenna as well. So the question is, how can we reduce the complexity of these antennas when it comes to IoT applications? That's a question from Sandra. Thank you, Sandra.
Okay, thank you so much. Well, this is a very tough question. Well, we can use small antennas at the cost of a smaller efficiency of the antenna, or a smaller gain of the antenna. There is not too much that we can do about it. The other approach is to use an inductive link, for instance. It's what we have used in our latest applications for extremely short-range connections, and that is also a possibility. And by doing that, of course, the source and the circuit must be at an extremely short range, and but it's also an alternative. Otherwise, we have to live with this antenna sizing, which is always, let's say, larger than the circuit itself, of course.
Okay, another question from Luis Jr. Thanks, Luis, for your participation. His question, Professor Jorge, is regarding slide 16, where you had this solar thermal DC-DC conversion structure. Luis Jr. would like to know why the capacitance input, CIN, is used, and also if it is integrated on chip, or if that capacitance is external to the chip, and that's related to slide 16 on harvesting, energy harvesting.
Okay, so to have a capacitance set input somehow acts as a decoupling capacitor or low-pass filter already at the input. So it can be external or internal, depending on the levels of energy that we are talking about. It may, you may discard it if you want, but at the end is an important circuit element at the input in order to reduce the variability of the source. At least it will make some voltage, let's say, tank there, some charge tank that will represent a voltage for the rest of the circuit. And if I recall by heart well the circuit, it is also that voltage is also used to supply the startup circuit of that paper, I would say. Okay,
another question from Professor Lucas Severo from Unipampa in Alegrete. Well, he congratulates. It's a very interesting talk. The question is, you, Professor Fernandes, have shown the use of a forward bulk bias to reduce VT and to improve the switch's performance on the RF to DC converter. Lucas Severo's question is there a similar strategy when using SOI or FinFET device, without which, of course, we don't have the bulk adjustment of the threshold?
Well, if we look at SOI, well, I have not designed any, but SOI by nature has the bulk as the backgate, which means that the bulk will act almost as a second gate source node, and will in fact make let's say the transistor fourth terminal more heavy to have more influence on the ID VGS on the ID voltage curves. So in fact, I would say that with SOI we would definitely benefit from it.
Okay. Another question is from Sandro Ferreira from Unicinos. He, thanks you for a very nice talk indeed. Regarding now the impulse radio ultra wideband, regarding the synced on-off key modulation, OOK, how does it compare to the more traditional approaches regarding power consumption? So he's asking about the modulation and how does it compare with other approaches?
Okay, now I'm reading the question. Okay, so one of the advantage of this synced modulation is that it's very reliable towards process variations. So when we do impulse radio ultra-wideband circuits, if you look at the classic, let's say classic application of it, the standard obliges us to do the spectrum based with the 1 megahertz bandwidth resolution. So with 1 megahertz bandwidth resolution, the most efficient pulses where we can obtain larger voltages are usually, it would mean that we could only have like 1 megapulse per second, because with 1 megapulse per second, we are still in the edge where we have 1 pulse for each microsecond, or 1 pulse in a 1 megahertz bandwidth. So usually for IoT, this is more than enough. And if we have this OK modulation, this synced OK modulation, we only reduce 1.5 times the average pulse rate that we can obtain. So that is probably the most the better way to do it. Any other will use more bandwidth, because it will use more bandwidth. No, it will reduce the data available, or it will mean that the amplitude of the pulses will have to be smaller. And then it's not a linear thing. They really have to be smaller, because then we have, let's say, 2 pulses in each microsecond that are being averaged by our spectrum analyzer.
Okay, well, before we go to the next question, I would like to insert a very general one regarding the ultra-wideband, narrow range, power efficient communication. It seemed that a few times, about 10 years ago, there was a lot of excitement on ultra-wideband for short range and power efficiency. But for some reason, the interest in the community of integrated circuits decayed on this subject. And while Bluetooth low energy and other non-standardized commercial protocols for IoT start to gain grounds. So why do you think is the reason why there was this waning down of the interest on UWB? So it looks like the commercial scene, commercial arena didn't go for it. We have a general idea, and then the next question will be on the DC-DC conversion. So what's your suspicion about this, Professor Jorge Fernandes?
So my opinion on this is that there was an expectation that ultra-wideband would be able to reach a few meters with extremely large bandwidths. And the problem is that as we go away from the source, the signals become too small. The receivers become more complex because it's not a continuous wave signal. So it's not so the receivers become more complex, also more power greedy, and therefore the communications really decay a lot. And I would say that this difficulty in design a very efficient receiver for this kind of signals that would allow, let's say, to operate at a large distance without too much of a very high power consumption, also decayed the interest of it. There was also the idea that it could be used in an extremely short range. And by extremely short range, I mean those things that we can almost just contactless applications, but at very high speeds. I don't know what is the state of that right now, but that was also a target application of this technology. But again, it's difficult when you have different nodes and you have to do the other levels, the other layers of the OZ system in order to establish communication with multi-nodes and so on. But I still think that for short-range direct applications, they have the advantage that they really have extremely low power.
Okay, well, one final question is regarding again the rectifier circuits for ultra low voltage, ultra low power. Paulo Cesar Aguirre from Unipampa, thanks you for your excellent talk. And his question is, the presenter rectifier generate around 1 volt. So his question is the power efficiency kept if the output voltage is set to around half a volt, let's say? What is the general trend for low power IoT circuit? Reduce the VDD of all blocks, or energy harvesting producing VDD around 1 or 1.2 just because maybe the efficiency is better. So his questions are regarding the ultra low power IoT and this harvesting issue in the CDC conversion issue.
Okay, when we are talking about 1 volt, let's say it's closer to a standard, or let's say to a voltage that is commonly used on today's microelectronics. So many technologies have 1.2 volts or 1 volt of power supply, minus plus 10%. So many circuits target that voltage. That was solely the reason why we also target 1 volt at the output. Of course, it can work with 0.5 volts or less. So we have showed that we could obtain around the power harvest started, our power harvesting. I'm not talking about the general power harvesting circuits, but in our case, the circuits were very efficient at 0.4 volts. So they were already stable at 0.4 volts.
Okay. Well, the very last one, Mateus Moreira, just asked, if your LC oscillator topology looks to have only 6 bits of control for the LC oscillator. Is this because you have very large transistors and the capacitance from routing becomes a problem for the frequency range?
No, the main idea of the circuit was again to be the control bits had two goals. One of them was that we could choose the frequency where it would appear in the range between 3.1 and 10.6 gigahertz. The other was to compensate for process variations without any further calibration of the circuit or the need for a crystal clock or whatever. So being a pulse, we just need the frequency to be on around a certain range. It's not like it is dependent on the frequency itself. It's not like a narrow band communication issue. So we just need to have it more or less in the band of the receiver. So we can assume some variability there, and we can just have a few bits that will place us in the middle, in the lower, in the upper end of the window that we are allowed to, and to control it slightly for process variation.
Okay, well, that comes to the end of the talk. I would like to thank, on behalf of all the team who organized the distinguished talks for solid-state circuits and EDS, to thank you very much for your very nice talk. The audience here reached at the peak 110, 120 people, and they all thank you for your kindness and attention. If you have any let's say, site in which you make these slides available for the chapter or for the interested people, please let us know. We will make sure that we'll distribute that for the chapter members and the audience. Again, if you are out there listening, and ask people to subscribe this YouTube channel here. That's the Solid State EDS South Brazil channel, which is link is in the screen. And the next distinguished talk and webinar will be given remotely by Professor Paul Jaspers from Leuven in Belgium. He will talk about systematic design of analog CMOS circuits with the methodology that he developed in the book. He's an IEEE fellow, and I certainly will enjoy his lecture on July 9, 1:30 at UTC -3. Okay, and again, join IEEE, and if you are South Brazil, join the chapter activities. We thank you all for your attention. I call your attention that we have several series of talks being hosted here by sister societies like CAS. There will be a talk tomorrow, sponsored by CAS Society and CEDA, done by Patrick Groneveld. That was advertised at the beginning of this video. You just go back to the beginning and you'll see the postcard and time for tomorrow, 1:30. Tomorrow, that means June 26th. So I'll be seeing you July 9. And again, thanks on behalf of our chapter. Thanks a lot, Jorge, and thanks for your presentation, okay? We really are very happy to be in touch with you. Last words are yours.
It was my pleasure. Thank you so much. And I hope that next year we can do this in person, close by. Okay.
Certainly will be our pleasure indeed to have it, and be aware that we have a electron device talk on July 30th at the same YouTube channel, but now a different time because the speaker is coming from China. So thanks a lot, and thanks for helping the Solid State Circuit Society EDS activities. Thanks to the speaker, and have a nice day or evening to every one of you. And please stay tuned and safe. Bye-bye.
Bye. Thank you.